There's one thing that I forgot to mention in the last slide. It's important because we are going to use this notation over and over again. This is a linear transformation of u by an operator a to another vector f, and this is the symbolic way of writing a differential equation, and this is called the strong form of the problem, which, if A is a symmetric, strictly positive operator, has a unique solution in D. So this is called the strong form of the problem, whereas this, in terms of the inner products, is a variational statement, which we also called a weak form. A weak form is not necessarily weak. Minimizing it would give you the same answer, u equal to u naught, as this would, but we will use this notation, strong form and weak form, from now on. So weak form is something that we minimize. It's an integral statement. It's an inner product statement, whereas a strong form is a differential equation. So let's take a problem, and this is the first problem. So consider a differential equation. Don't worry too much about where it comes from. So this is a differential equation, and this is for a cable, and ax is a function that we will see. For us, we will take ax is always greater than 0 everywhere. So ax is sort of a tension in the cable, and it's always, the cable is in tension, so ax is always greater than 0 from a physical standpoint as well. D is my domain. It's a 1D case, so D is my domain from 0 to L, and at the ends, u equal to 0 and u equal to L, the values of the function that we need to determine are equal to 0. This is how it's given. F lies in L2, F lies in L2 or in H0, and D is therefore a subset of H0. Now, we have to find the weak form for this problem. To find the weak form, we first have to identify the operator. The operator in this case is A, which is d dx of ax dx. This is the operator, so that au equal to f is my differential equation. Now I will have to prove that this operator is symmetric or self-adjoint, which means this is equal to this. So after I have proved the self-adjoint, I will have to prove that au comma u is always greater than 0. And when I'm working with L2 or H0, then I know that this inner product is defined as, from 0 to L, it is defined as au to v dx, which means d dx of u dx, so that this is au, times another function vx dx. So this is how the operator is, the inner product is defined as. So now here we can now apply integration by parts. First, we get we integrate this, so we will get minus ax du dx times v at 0 and L plus, so the minus and the minus become plus, and we are left with 0 to L. Now derivative of this, dv dx times ax du dx dx. Now all these functions u and v that you choose have to come from the set of admissible functions. So they have to have, at 0 and L, they have to have 0 values, which means that V also will have to have V0 equal to 0 and VL equal to 0. So this will be 0, and therefore I am left with this is equal to 0 to L AX du dx times dv dx. So this is what I'm left with. And you can immediately see a couple of things, that if I interchange u and v, this remains the same. So I could have as well started from AV times u and I would have reached the same point, right? The other thing that you can see is if I now put u and v to be the same, so this becomes du dx whole square. So au comma u becomes ax du dx whole square, and if a is always strictly positive, this quantity is always positive. Therefore a is a as given here is a strictly positive operator, and I can write down the variational principle right away as in the previous. So I can write half au comma u, so half au comma u is this guy, minus f comma u, so minus f So this would immediately be my variational principle. Minimizing this would be equivalent to solving this example, solving this differential equation. So, so that's what I have done here, and this turns out to be my variational principle. Let us do another problem in the next installment.